you have a ton of data, and maybe you only need that little bit. Often you can do that before the data even hits R. And so I'll go over how to do that in some concrete ways. It seems like a simple thing to do, but yeah, often like one of the ways you can make data smaller is to load it into R and filter it and make it smaller, like you would with a CSV or something like that. And you can do that with spatial data too. Another thing that will show up throughout this talk is looking for the spatial join. Um, Spatial joins, much like regular joins, uh, are when you have two different tables, and you're looking for the interaction between them. And for a regular join, if you're like, joining on some common column and you have a name in one column and a name in some other table, and you're trying to join them together, and look at all of the things, look at the data as one, you'd use a join function. Spatial joins are provided by a number of different databases and packages, and phrasing your problem as a spatial join can often make a huge difference. So here we have a bunch of points, and I'll go through an example that is almost identical to this in a few different frameworks today, but we have a bunch of points. Those points in the data today are elevations. So we've got a whole bunch of point spot elevations in Nova Scotia and a whole bunch of lakes in Nova Scotia. And we like to assign some elevations, some probable elevations to these lakes. So what you would kind of visually, it might be a little bit easy to figure out what to do. Like you find the intersecting or the contained elevation points, and then you might take a mean of those. So that problem is a spatial join, and how to phrase that spatial join, and knowing when you have a spatial join critically is a great way to speed up your workflow. And yeah, we'll talk a little bit about that. Yeah, here's some join examples, and you can look at those when I post these slides. Um, there's another concept, parallel processing. Parallel processing in R is I find it hard, and it's probably gotten a lot better since I was doing this on a regular basis. But still, the most effective way to do this, or the most effective time to employ this is when you have a bunch of files. So like the trick with parallel processing is getting something that's already read into R and into some other parallel processing thing. So like if you read in a huge file and you want to process that in parallel, it's pretty difficult to send that entire big thing to some other R process and execute these things in parallel. But if you already have files, like that is trivially parallelizable from R's end of things. So here's an example, and there's a more concrete example in a second, but there was a workflow I was working on a number of years ago at Fisheries and Oceans Canada, and it quite literally we were provided hundreds and hundreds and hundreds of files, and we were rasterizing those files and then combining them into some result. But the part where you went from here to here, like the geo package to the TIFF file, the part where you rasterize it, there's no reason that can't be done in parallel, and there's no reason that R can't orchestrate doing that in parallel. So I think I used per, maybe like or fur, maybe is like the future per thing, and I think that's gotten a bit better, and there's some exciting things coming there too, with Mirai and per. But yeah, this is the ultimate endpoint of what I was producing in that workflow. It was an animation. We had ice coverage from the Canadian government, and it was provided as like E00 files or like shape files, like there was all sorts of stuff. And so we had one where we cleaned up all those into geopackage files. And then we had another step where we took all those and we made them into TIFF files. And then we had another step where we aggregated those by time window so that we could have sort of like a time aggregated, completely aligned, pixel aligned netcdf file, because the researchers we were working with were oceanographers, and oceanographers love NetCDF files. And that's not a dig on NetCDF files, but yeah, I'm always entertained how many people are willing to squeeze certain types of data into them. But this was an example, and we were able to do that. And we had this massive supercomputer at our disposal. And if you have 54 cores, then processing hundreds of files is actually not that bad. So that was how we set that up. And when I post the slides, there'll be a link to that project. But yeah, the parallelizing, when you can phrase your problem as like, I'm converting this one file into another file, and you have a lot of files to start with, that type of problem is quite nicely parallelized. Yeah, another concept is embracing the not specialness of spatial, and that's like my company's tagline. And so I definitely I spend a lot of time thinking about that these days. But it is true. Like in the spatial world, you have a geometry, and that geometry is the center of the universe, and like that geometry can have attributes associated with it, but they're the geometry's attributes. They are not the attributes geometry. And that works great in certain contexts. And a lot of spatial file formats are certainly make this assumption that you have a geometry, and that geometry has attributes. But if you think of them as equal, then you can unlock a lot of really fantastic and much faster workflows. And the reason for this is mostly that I think I said 1 to 50 here. I'm not actually sure what the ratio is, but there are a lot more people that are working on optimizing table operations. And so if you can put your geometry as part of a table, then you can take advantage of those. And if you pretend that R is the center, or the R is the center of the universe, obviously, but if geometry is the center of the universe, then you can't use a lot of those things. So working with spatial databases, working with Arrow and Parquet, and even working in R in data frames that aren't SF data frames. If you can unlock your problem to be part of that, that can often be much faster. Here's just an example. We'll show an example later on where we read in this elevation file. This is about 11 million elevations. 11 million is like not actually that big of a file in the grand scheme of things. Certainly with the word data that I work with now, and like 11 million sure sounds like a lot of points. But yeah, it takes 1.5 seconds to read in if it's in a Parquet file. We'll show an example in a second. If you try and read this in to a try to read this in using SF, just like naively using a flat GeoBuff file, which is a pretty fast file format. It'll take you, I think, 200 seconds or something. It's like a couple of minutes. So like these tools, people have optimized them pretty heavily. And so if you can phrase your problem so that it's no longer spatial, at least for part of it, then you can make your workflow possibly a lot faster. Also important to know that having geometry be the center of the universe when you're doing a spatial analysis can be incredibly convenient. So a lot of the things that I'll talk about, the concrete examples that I will talk about, involve, leaving this world for a little bit, but then coming back to it. So if you're often, you might do something where you run some part of your analysis in a database, and then you bring it back in, and then you have an SF data frame. Geometry is the center of the universe again, and you have all these tools and at your disposal. And importantly, it's a tool that you understand. So, every single one of the things that I will talk about today involve trading some verbosity. So you have to write a little bit more code, and you get in some of these cases you get a huge performance gain. But like if your job is running in less than 10 seconds, or if your job is running in less than 30 seconds and you don't mind, then like you don't need to optimize it. And trading that verbosity is probably not worth it. So yeah, so here's some of the concrete bits that I'll talk about. So the first sort of and these are vaguely in order of the things that I would turn to. I work on spatial databases now, and so I think now I would probably turn to spatial databases sooner. But certainly I spent a long time avoiding them. And so hopefully I can convince you today not to avoid them. And the landscape has gotten much better. But yeah, I think the first thing that I usually would do is I'd be working in SF, and then I would sort of use some of the like notice that my analysis was taking a while, and try to optimize some things specifically with SF. Like no need to leave this nice cushy geometry world where geometry is the center of the universe. Uh, we can we can still use these tools. And then I spent a long time, and these are in this package list. These are some of the packages that I developed, but sort of working beyond SF. So leaving the world of the spatial, the simple feature, and working in a place where geometry is a column, and that there's a couple of different ways to represent that, and some of those ways are more efficient. In some cases, a lot more efficient. So then that was kind of the next thing that I would usually do. Like, okay, let's leave SF for a tiny bit and do this, and then come back to SF when we're done and write our files or write our output, that kind of thing. And then finally, and this is something that I only came to love recently, is driving a spatial database from R. So R is still my tool of choice if I have to get something done. I pop open R, and R has lots of integrations, and it can drive a lot of tools. And the ones I'll talk about today are Apache Sedona and DuckDB and PostGIS. There are more. Many databases have spatial functions, but the concepts are largely the same. And the trade-offs are largely the same. Like you trade nice cushy R code that you know how to write and into SQL, which I didn't know how to write for a very long time, and only got good at recently. And yeah, you have to figure a couple of things about how to get stuff in and out of database, but you can run a lot of things a lot faster, depending on what database you have. So yeah, let's talk about two concrete examples and just using SF to make things a bit easier. So we're going to go over the filter on read thing. So like just make your data smaller on read. So here's an example. This is a bounding box sort of around a place called Gasper Lake and near Wolfville, Nova Scotia, which is where I lived for many years and canoed for many years. And there's a whole network of lakes and rivers around there that are fun and interesting. So if you just read that file and just a blind read, and then if you filter it to your area of interest, so here's the read part. Here's making sure that our bounds match our file, and here's doing that filter. So this results in a data frame that a simple features data frame that has only the features that I'm sort of interested in. This small area of lakes in Nova Scotia, but that takes about over a minute to do. So you can flip that around a little bit, and you can use this thing called WKT filter in STRead, and that will filter it on read. Many of you might know this trick already. I didn't know this trick for a very long time, and I refigured out how to do it for this talk because this concept is something that I spend a lot of time trying to figure out how to do automatically in a spatial database. And we'll chat about that in a bit later. Yeah. So yeah, you can filter on read. It takes a lot less time. This is 7 seconds, and before it was taking over a minute to read. And this can actually be quite a lot faster depending on this particular file does not have a spatial index built into it, or I wrote it without an index. But some file formats do have indexes in them, and then they can perform this read quite a lot faster. Yeah, that's my first concrete trick of not leaving SF. So my second trick is the join. And it also took me a long time to figure out what a spatial join was and how to use one. And again, now I spend almost all of my time optimizing them. And so they're important. And learning how to phrase your problem as a spatial join can be a bit of a trick, but recognizing when you're in that situation um, is important because then you can ask the right questions. When I was learning this, we couldn't ask a language model about anything, and now if you know, you can now ask uh, a large language model to write a spatial join for you. But if you don't know you have one, then it's tricky to make that happen. So yeah, here we're going to look at the interaction of the elevation points with the lakes. So if I have this lakes layer, this lakes data, and I want to have some vague notion of elevation for these lakes, um, then this is a totally naive way to do this. Like, okay, I've got a bunch of these lakes. Like, let's loop over all the lakes. Um, let's find the intersecting elevations, and then let's take the mean of those values. And it sounds like a great idea. And it is not a bad idea. If you don't have that many points of data and you understand what's going on, then this is a great solution. The problem is it takes a hugely long time, even for this very small area. Like we've already made our problem smaller, in both from the lakes direction and from the elevations direction. But we've got this, it's over 200 seconds. So it's like a couple of minutes. I went and got coffee when I ran this. But this is a join. We have one layer over here, and we have one layer over here, and we are looking for the pairwise interaction between the things that actually touch each other, or intersect each other in this case. So the function for that is stjoin, and you can do a group by and a summarize, and that will get you, yeah, that will get you a result, the same result that you're looking for. And again, recognizing that you have one of these many-to-many problems is the barrier. Knowing how to rate one is less of a barrier, particularly these days. But even you could probably Google this a long time ago. But yeah, recognizing that you have a spatial join, you are trying to find only the pairs of geometries that are interacting with each other. Usually it's intersecting. You can do other things like containment or touching or some of the various other predicates, but intersecting is the big one. So yeah, there are also some times where you need to move beyond SF in order if you want to stay in R. And one of those ways that you can move beyond SF is Terra. Terra was developed a tiny bit after I spent a lot of time doing r-spatial work. So I don't know all that much about Terra. There's some excellent chapters on geocomputation with R about this, or at least some chapters in it. And you can do reading with extent as well. And there's a lot of other things that you can do. I primarily would advise somebody, and again, I haven't spent a lot of time in Terra, but I would advise using Terra if rasters are involved. You can use SOF and you can use stars to work with rasters as well. Terra integrates rasters as a bit of a deeper level, and there's a lot of great things that you can do with Terra. But like Terra will not do a spatial join for you. And one of the things that I probably should have led with is that I spend a lot of time in the vector world. I don't spend a lot of time doing raster work these days. So yeah, maybe perhaps there probably should have been some a call for suggestions about those as well off the bat. And yeah, so this is great. One of the things about Terra is that once you are in Terra land, it is fast, but you have to stay in Terra land for it to be fast, as I found. And perhaps there's some tricks that I don't know about. Yeah, so the WK package and some associated packages around that. The WK package is one of the packages that I wrote, so I feature it here, not because I think it's the best or because it's awesome, but because I happen to know it very well, having written it. So the WK package and the geos package, they have a bit more liberal version of what geometry is. So I wrote these around the time that the vectors package was written. And these basically provide a vector class for different types of geometry representations. So if you want to just keep some raw well-known binary hanging around, which are a bunch of lists of raw vectors, that can be quite fast. Or if you want to represent geometry as an x and a y, the WK package gives you a way to do that. And again, this sort of is leaving the world where geometry is the center of it all, and where it's just a participant in a data frame, and it can be a lot faster. So yeah, there's also the Vapor package, which is by Michael Sumner, and that will let you read from GDAL, and it reads from GDAL in a way that you can get it sort of directly as well-known binary. And again, like we're trading some verbosity and some nice bits for speed here. This is an example. This read is actually not any faster than the filtered read for SF, but we're reading in this entire elevations file, all 11 million elevations, and we could read all of them in without filtering them. And it just turns out that the workflow that we're about to do, it's actually no faster to filter them. So, like, if your computer has enough memory to do it, and you don't need to make your problem smaller, then don't do it before you have to. So, yeah, this tool is fast enough that we can read it all. And we're going to go straight to geos here. The geos package is a more thin wrapper, a literal wrapper around geos, whereas SF uses geos, but it abstract like it. There's quite a few layers between U and geos in SF. So the geos package provides you, almost no line between U and geos. So that's great if you know what you're doing with geos. And one of the things that we're going to do is run a join here. We can run a join, manually. And that join runs about 4 times faster than the SF join. It can run quite a bit faster also. And the more that you are able to reuse this index, which is a way to search for locations very efficiently using on all these 11 million points, the more you're able to reuse that index, the more benefit you'll be able to get out of this. So this is only iterating through a couple of lakes. But if you have, the lakes for, I don't know, an entire country or something, and you want to process that, in chunks, then you can do that, and you can reuse this index all the way through. Yeah. So again, this is trading some verbosity. Like, this is not as nice. I am 100% willing to admit that. But you can do some things much more efficiently. Yeah. I guess one of the other things I wanted to talk about with WK is that, so I'm using the geos geometry here, and there's read WKB. The WK package also provides, XY for points, which is a big one. If you're able to store, if you want to convert your 11 million points to X and Y values, the WK package will do that. And once you have them as X and Y values, then all you have is a table with 11 million rows. And that's actually not that many rows, even for R. So yeah, and finally, we're going to talk about spatial databases. And spatial databases are what I do now, and I love them. But I didn't know anything about them for a long time. And I've come to appreciate them in a profound way, I guess. So yeah, spatial databases, the main thing that they can do for you is that they take care of all of those tricks that I just talked about at the very beginning, all of those concepts. Those are all built in to spatial databases, good ones. And if they're not built in, then they will be soon, or they should be, and you can complain to the maintainers if they're not. So things like making your problem smaller. Databases have a way to look at your query and look at your st-intersects call and say, okay, this query is only going to affect points that intersect this because I know the user typed this. And they will only read part of that file. And they know how to build an index on a spatial join. They can look at the data on either side of that join to try and figure out which side is more efficient to build the index on. They can do things in parallel. Spatial databases and databases in general have spent, are the product of many decades of development, and they are really good these days. So things like Apache Sedona, DuckDB, PostGIS are the ones that I'll talk about. But the Oracle and I think MySQL has some spatial functions in them too. Lots of databases have some of these, and you can get some benefit out of them. They also introduce some problems. So you have in R, it's very easy. Like you can read data in, and you have a data frame, and it's sort of a known quantity. If you're an R programmer. If you have a database, you have to get that file or that data from your process into the database, which is usually sitting somewhere else. That can be tricky to do, and it can be tricky to do fast. You also are going to have to type some SQL. I know that there are tools like dbplyr that will write some of it for you. I have not had a lot of luck getting all the spatial stuff to work out of the box all the time. Perhaps other people are better at doing this, and it's if anybody has a great resource on this, I would love to post that for everyone. But yeah, I have mostly found that what I would like to do is type a tiny bit of SQL into my database and let the database execute this thing, and then once the problem is small enough that I don't need the database, I would like to bring it back into R and work with it there. Because I'm better at R. Like I know R, how to program in R, and I'm not awesome at SQL, or at least I didn't used to be. There are also, you have to choose a couple of things. You also have to choose how you're going to drive that database. So you can use dbplyr to do it, DBI, which is the older school, but still standard for doing this. And ADBC, which is one of the things I work on. And I was actually pretty excited that to be able to come up with an example for PostGIS and ADBC. Yeah, I'll show you in a second. So yeah, here's DuckDB. So there's a couple of things about setting up DuckDB to work with spatial. DuckDB needs an extension. So you have to load the spatial extension. You can also install spatial if you haven't done this yet. And this is an example of driving a database using DBI. So these are all these old school S4 camel case things are using DBI to drive the database. And this is a brand new thing that I'm pretty excited about, but also one of the things that I added to DuckDB. Spatial is this thing called registered geo extensions, which basically enables you to get data from a database out into R and SF much more ergonomically than you used to be able to do. So yeah, let's get some data in to DuckDB. DuckDB spatial is fantastic in the sense that you can select all from a flat GeoBuff file. This also works with GeoPackage and shapefile, I believe. And there's also a function I think you can do select all from like read GDAL, or maybe stread, I forget which one. But there is a function in the spatial package that can read any GDAL data source, just like SF. And yeah, this is great. So when you're creating this table, this is a little bit like creating a variable, but in DuckDB land. So in R, we would be, read lakes arrow, read SF, this file. In DuckDB, we're creating a table. That's a database. Everything's a table. Just how it works. And you can create a table with filtering. So you can filter with st-intersects, and you can. It's a bit of a trick to get a literal, so like a known static value in your query. But I'm using glue to do it here. I find that you can also do a parameter, like bind a parameter, but it's a little bit trickier to do. So I do this. Yeah, we'll create our elevations table as well. And this actually does read. So like this will read everything in and create it in your DuckDB connection, which is sort of your house, your temporary house for DuckDB stuff. So you've created this temporary lakes thing in DuckDB land and this temporary elevation thing in DuckDB land. Yeah, and after that, you can run your query. And doing a spatial join is like doing a regular join in a database, but if you don't know how to do that, which I didn't for a long time, that won't help you. But often, these days particularly, if you're able to Google doing a spatial join, the spatial join syntax is also the same in just about every spatial database there is. So you're joining, and you say you're going to join on st intersects. And this will give you and again, we're doing a group by and a summarize. And SQL is so funny because you have to, everything is backwards. You have to type all this stuff backwards. But this will get the job done. And this is very fast. I think this ran in, I don't know, less than a second. It includes all the parallelization and all the reading, and all that can be done kind of all at once. Because databases are smart and they spend a lot of time trying to optimize these things. Yeah, so here's an example of getting data out. And I'm particularly excited about this example. I spent a lot of time working on all of the pieces and getting all the pieces available in all the places so that this just works. And so I was pretty excited when I typed this and it worked because I'm not a user. I don't try this very often. Yeah, if you'd like to execute some SQL and you want to get it back into SF, then it's very easy to do that. You do need this register geo extensions thing. Yeah, so let's talk a little bit about PostGIS. I called it PostGIS for a long time. I think PostGIS is the accepted terminology these days. But most of the time I just read these things. I'm going to use the ADBC to read it. So ADBC has a Postgres driver, and again, I'm giving you examples of things that I know. I maintain this package, and I wrote a solid chunk of the Postgres driver. And so obviously I tried to make sure that it would sort of work for spatial, at least a little bit. And ADBC, this is an example of a slightly different way to drive a database. You can drive a database using DBI, which is like DB execute, DB get query. ADBC you can only do three things, really, if you don't want to be very verbose. You can execute, and you can read, and you can write. And so we can create a table. We're creating a home for these guys. And you can write those tables in, and you can use this append mode. Here we have a friend, the WK package, helping out to make sure that we have this thing as well-known binary. And yeah, all of these things kind of come together to make it so that you can get data into the database. This is faster than any other way that I know about to get a huge quantity of things into a Postgres database. That said, I think that there are probably other ways to do it. I just don't spend a lot of time with that. I know that our Postgres package uses a very similar mechanism to do this, Postgres copy. It could work too. But one of the things is a lot of these things don't special case spatial. And so it's sometimes tricky to work. But this will get you quite a lot of data into a database quickly. You can create a spatial index, which you need to do in order to get a join to run properly. The fact that you have to do this manually is something that is a bit tricky about PostGIS, but you do have to remember that making an index, particularly for geometry, if you're about to do a join, is kind of the only reasonable way to get a decent speed on your join. And finally, you can run the join. This join looks the same as the other join. It's the same syntax. And yeah, you can read ADBC will get it out, and AsTibble will get it as a data frame. And I don't think I have an example of getting geometry data out. It's a bit more complicated because the ADBC driver doesn't understand the spatial type. But it's very similar to the DuckDB example. Yeah, and finally we have Apache Sedona, and I'm not going to give you an example, a live example of Apache Sedona, It is very similar to driving DuckDB, although I think that you have to use sparklyr, which is great because it integrates a little bit better with the SF syntax and dbplyr. So I put the link here of the getting started vignette. It's excellent, and yeah, it'll get you going. So yeah, I didn't quite get a chance to post these slides in advance, but I will. And this repo is live, and I'll post this link in the chat in not too long. That has a copy of these slides. And again, yeah, I'd like to collect some of the comments here and yeah, and write a blog post about some of the stuff. So yeah, I also want to end with some acknowledgments while Jesse's getting ready with questions there. Edzer asked me to write the S2 package, help write the S2 package a long time ago, and this really got me started working on all this stuff. Michael Sumner has been a fan person and cheerleader for a very long time, and also if there's anything that I know that Michael Sumner has done it first. Whenever I get something, he's always invented it first. Josiah, Jesse, and Terry have been great hosts for this, and Hadley was an excellent mentor when I was working at our studio on ggplot2 for a few months. Yeah, and largely the contributors to r-spatial, which really make the community what it is.
Dewey, thank you so much. I think we got some real hot tips and very specific information for working with spatial data. We do have some questions that have come in, and everyone, if you haven't asked your question yet, you can use the Q&A icon to ask. Dewey, I'm going to read a couple of these out loud and see if we can get some responses from you. The first one is from Anonymous. Can you elaborate more on why GeoArrow support in DuckDB Spatial helps with ergonomics with R specifically? How did the lack of GeoArrow in DuckDB Spatial make it more difficult to work with downstream R objects, like, for example, SF or Terra?
Yeah, that's a great question. And it was a lot of work. And so, yeah, it is a question of whether it was worth it. I think that it is. And one of the things that I work really hard with in my work in Arrow and my work on spatial databases is I want to make sure that geometry stays geometry. So like if you have a geometry column in a database in DuckDB, then I would like it if when you got that data out into R that it was also geometry. And ideally, it would also keep the CRS with it. And it would be a sort of seamless transition between the two tools. And so the GeoArrow support is really about ergonomics. Like there are workarounds. You can call st as WKB on your output, and you can wrap your input as well in binary and then in the other direction. But functionally, if you're using Arrow to interact with DuckDB via ADBC or via to Arrow or from Arrow, then geometry, when it's geometry sitting in R land, it gets transformed into Arrow as Arrow geometry and then can go straight into DuckDB. And DuckDB knows it's geometry, and it's really about ergonomics. Part of those ergonomics are for the user, and part of those ergonomics are just like error proneness. Like DuckDB doesn't happen to do anything with CRSs. Like DuckDB will ignore your CRS completely. And I didn't put that in the example, but it will drop your CRS. So you have to be pretty sure about your spatial metadata before you get in there. But when it does support it, and I have bugged Max quite a lot about this, when it does support that, your CRS won't get dropped when you have it go in or when you put it out. When you put your data in or out of the database. So that eliminates some classes of bugs, like trying to select something with the wrong CRS. So yeah, it's a little bit about ergonomics. It's a little bit about safety in terms of making sure the spatial properties are propagated. And yeah, I think it'll make a bit more sense once DuckDB supports CRSs and some of these other spatial databases have built-in support for spatial metadata. It's also a lot faster to get data in and out of DuckDB using that.
Okay, fantastic. We have some more. This is also from Anonymous. When performing a spatial join, is it necessary to project all databases into the same coordinate reference system? If we have a reproject, if we have to reproject data back and forth between different systems, could that affect the accuracy of the join results?
Yes, that's an excellent question. And that's an example where living in SF land will help you, um, because SF will not join two layers if they don't have the same CRS. Um, and in the example that I gave here, I did reproject the less expensive one into the same, into the same projection. There are some tricks about that if you have one. Sometimes you can only do reproject part of it if you are iterating through. But yeah, in general, you really do need that st intersects call to work on two things that have the same CRS.
Okay, fantastic. This is from Matthew. How do you see the geo arrow package fitting into this with and without the use of spatial databases?
Yeah, another great question. GeoArrow itself is actually doesn't do anything. I mean, it does do some things, but like it's not there to compute. It's there as glue. So in the GeoArrow example, like the reason that I had to library GeoArrow before using DuckDB's like arrows to arrow with DuckDB is because it registers some extension types with arrow, so the arrow knows how to propagate that spatial metadata in the spatial type. So and it has like STS SF on arrow objects. Um, so that example needs GeoArrow to work, even though GeoArrow is really behind the scenes, just providing the right conversions to make sure that everything makes it through properly. Because working with databases, getting Arrow is a great way to get stuff into and out of databases in a performant way. And so GeoArrow, that's where GeoArrow fits in. So it really works best if you're working with ADPC, which is arrow based, or with your working with DuckDB, which has arrow integration kind of built into its DBI interface.
Okay, fantastic. From Dane, where would you use Rust packages like RSGeo with geospatial data?
Yeah, RSGeo is awesome. That's in the category of something that I think is very cool and haven't had a chance to use yet. Um, and yeah, I think RSGeo is built on the GeoArrow memory layout and uses GeoArrow's sort of uh, framework, but provides a lot of more compute functions. Yeah, that's in the category of something like geos or S2, whereas you sort of left um, geometry is the center of the world, and you only have a column and a data frame. Yeah, and I think the RSGU provides functions that are often faster. Uh, I haven't used them, but I know Josiah has worked really hard on that, and I'm looking forward to it. And yeah, I'm looking forward to it.
We have a second one from Dane as well. Are you aware of any 3D geospatial libraries for use in R, especially for large data sets?
Yeah, I mean 3D, the um, all the spatial libraries handle 3D in the sense that the coordinates can have a third dimension. Uh, and often you can use those as input and pass those into like you can pipe some of those data sets into like GDAL or some of the raster processing. But specifically like dealing with point clouds or specifically dealing with like graphics, um, I don't happen to know any point cloud utilities, but in terms of graphics, like that's where like Ratiator is really working. I'm not really sure that that's exactly where uh, yeah, I'm not really sure that's exactly where your question was handing. I think that there's also a CGAL wrapper, a CGAL wrapper. I think CGAL has some 3D things in it, but in general, like it is true. Like my examples are mostly like looking from the top down at the earth, and the third dimension is often a sidecar to that. Um,
Okay, next, from Anonymous. How do you decide when to use Sedona versus DuckDB spatial? Are there workflows that you can point to that you've used where you've used both?
Yeah, that's another great question. And so one of the things about DuckDB is that it's attached to your process. So like it's attached in your R session. All the memory is the same. And so when you're in that range where you're have been waiting for 10 seconds or 30 seconds, and you're like, what can I do to make this faster? That's often a DuckDB. DuckDB is often the answer for that. Using Sedona is often comes up when you are in a situation where you've hit that, like, I don't know, 5-10 minute mark, and you're like, okay, like this is going to take a while. Like, how can I throw more computers at this? And that's one of the things that Sedona is like exceptional at and unique in its ability to do, is that it can use more than one computer to execute your query. And DuckDB can't do that, or you have to work really hard or write your own parallelization logic. Sedona is, I think, that the only thing that I know about that can do like a truly parallelized join. Um, and so that is, yeah, it's really when you hit that 5 to 10 minute mark that it's worth looking at Spark, and it's worth looking at Sedona. And Sedona, of course, is geometry on Spark. So yeah.
Okay. From Anonymous, have you also seen Kyle Barron's Geo Data Fusion project? If so, how do you foresee it comparing versus DuckDB Spatial? Perhaps we could convince someone to work on a DBI client for data fusion so we could try this out in R.
Yeah, that's a great question. I work quite a lot with data fusion folks, and without saying anything more, I will just say that I think that it's the future. Uh, but all these things are have trade-offs. Data fusion has trade-offs versus DuckDB. They all have different features and ways that they integrate um, with R. And yeah, I think that there's some great opportunities for leveraging data fusion, which I think the geodata fusion project has really shown. I think that it's shown that this could be great. Yeah, I think that it has a great future, and we should definitely keep in touch.
Great. All right. From Michael, do discrete global grids, DGGS meshes specialized for the surface of the Earth, feature in the ecosystem? Are they on the radar for native support in Arrow?
Yeah. The answer is yes to both. So the one I'm most familiar with is the S2 one. So I am most familiar with S2 cells as grids. And in the S2 package, there's a vector class called S2 cell and a vector class called S2 cell union. And both of those things will get you, yeah, will get you, yeah, the ability to convert those things to and from geographies and intersect them. I'm less familiar with the H3 landscape in R, but I know that there's a package. And the other global grids I don't know as much about. I think that they're awesome, and I think that they're wildly underutilized. And if I had more time to work on the Minar, I would. And the DuckDB geography package, which I also maintain, yeah, there's an ST cell and an ST cell union as well there as well. Um, and yeah, the thing about them is they don't, yeah, getting them to interact with the regular geometries, I think, is a huge opportunity, um, because they're way more efficient. Like, they are geometry, they're just a representation of them that's much more compact. Um, and yeah, I'm probably not sure that I got to all of that, but definitely discrete global grids are supported in various places in R, but you do have to try a bit harder to use them. Again, it's in that category. Like, you've left SF, and so you have to try a little bit harder to get all these things to talk to each other, but you can get some pretty huge performance gains if that's what you need.
Okay, I'm going to do one last question here. This is from Michael. This is a raster question, so maybe not appropriate here, but what is the best practice for hosting large raster data online to facilitate fast and accessible operations using the VSI interface? As a single very large raster in a cloud optimized GeoTIFF format, as a set of similar tiles, each as cogs, something else? Do you have any additional recommendations for VSI access to vector data beyond what you've shared here? And is this equivalent, interchangeable to the database approaches you showed?
Yeah, that's a great question. Totally appropriate here. Definitely check my raster answer after I say it. I do see a lot of cogs. I do see a lot of cloud optimized geotiffs in the world. And there, we've got some folks working on AI, AI and inference, whereabouts, and they're probably going to kill me for trying to go outside my lane here. But I do, yeah, I see them using cloud optimized geotiffs quite a lot. Um, yeah, they can often be one big file. Again, the cloud optimizedness of them makes it so that even though they're one big file sitting on cloud storage, often that doesn't have to get actually read. The whole data doesn't have to get read. Whether you structure that as a whole bunch of tiny files or one giant file, I think is a matter of ergonomics for you. I have a feeling that if you make them too tiny, then the people downloading them will get mad. Um, Check that answer. On the vector side, yeah, I didn't talk a lot about GeoParquet, but GeoParquet is one of the ways that we can do this for Parquet, or sorry, for vector data. You can download only part of that data, and Overture Maps is probably the industry leading example of where where cloud optimized storage of vector data has been shown to shine. And like, a lot of those folks, Jake in particular, contributed back to the spec for GeoParquet to make sure that we could properly do that. But it was very successful, and you can query those Parquet files uh, with only downloading a small amount of them, and you can put these huge files up so that the size of your file on cloud is not necessarily the size of data that someone actually has to download. So yeah, GeoParquet is definitely the vector version of that. I still see a lot of cloud optimized GeoTIFF. I also see a lot of XAR in the world. And XAR is not as quite as compatible with the tools that I know about to work with rasters and R, because that's more of an n-dimensional array approach than a classic raster pixels with bands approach. But yeah, it's yeah, XAR and cloud optimized GeoTIFF are the ones that I see for raster.
Okay, Dewey, we're past the top of the hour, so I think we're going to stop here. There are a few questions we didn't quite get to, and I apologize to the people who asked them. But thank you very much today to all the attendees. Thank you from the R Consortium. Like I mentioned, we do webinars like this regularly, so we hope to see you again here. Dewey, thanks for all your time and effort and really fantastic information.
Great, thank you so much.
Okay, thanks everyone. Bye-bye.